In this lesson, we're going to sharpen our definitions of concurrency and parallelism, get something a bit more technical, which is going to help us when we get to those code examples. You're looking at the working file concur_parallel.txt, and I've got some verbiage that summarizes the points, but I want to focus on the very simple pictures. So to begin, let's assume we have a web server, and we have a bunch of client requests coming in, presumably from browsers, but they could be from other applications as well. And I'm going to define task 1 as the task that handles the first request, task 2 as the task that handles the second request, and so forth. So from the perspective of the web server, each incoming request represents a task that needs to be handled in some way or other. So what I'd like to do is to contrast two scenarios. In the first scenario, we've got an old-fashioned single processor machine, so all of the tasks have to share that processor. So some sort of time slicing is in play, and I've depicted the situation as follows. I've got a time span with a start time and a finish time marked, and then I've depicted down here the processing of the two tasks. So task 1 runs for a while, in my little depiction for 8 ticks of the clock. Each star represents a single tick. Then task 2 is processed. Task 2 takes only 4 ticks. Presumably we're just delivering up a static page or something that doesn't take much time. And then task 1 resumes to presumably completion. So maybe task 1 has to go against a database or run some sort of script, whatever. It takes a bit longer. Now, what we have here in this first scenario is concurrency. That is, we have overlapping handling of two different tasks, 1 and 2, but there's no parallelism. So it's never the case that task 1 and task 2 are literally being handled at the same time. What we hope, of course, is that the switching between the handling of the two tasks is so quick that it simulates true parallelism. In the second scenario, you can eyeball it right away and see, of course, that there's been a boost in performance. In particular, the throughput has increased. In other words, we're now able to complete the two tasks in less time than it took before. So this is a performance gain. Now the reason, of course, is that in the second scenario, we're assuming that we have multiple processors. For this example, 2 would be enough, assuming that one task can run on one of them and another task on the other. So the depiction down here illustrates the parallelism. Task 1 goes from the start time to the finish time, but task 2, by contrast, doesn't take anywhere near that much time. What I've done, by the way, is just arbitrarily placed task 2 someplace in the time span. It could be happening right at the start with task 1, but I've shown it a little differently here. It doesn't really matter where it occurs. The important thing is that task 1 and task 2 now are being done quite literally at the same time. So in the second scenario, we again have concurrency, but we also have true parallelism, which we don't have in the first. Now this very simple example is enough, I think, for the moment. This will get us started. As we get into code examples, these technical definitions of concurrency and parallelism are going to be refined naturally. In other words, in the course of working through the code examples, we will get ever sharper understandings of concurrency and parallelism.